All right, so we are going to start reading our thermodynamic tables, and you can access those tables as a PDF on the Canvas home page. There should be on the home page, there should be a button that says Thermodynamics Packet. Go ahead and click on that, and that will bring you to that PDF. The PDF you don't need to print out. You'll have access to that on exams, or you'll have access to the relevant portions on exams that you need for those tables. So just be familiar with them, be familiar with how to read them and how to interpret them. All right, so the ones that we're going to be looking at today are only for water. There are other tables and tables that are in that packet that are for other substances as well, for example, various refrigerants, but we're just going to be looking at water today. So I would just say be cognizant of what substance that you're looking at. So let's start with the saturated water tables. These are the ones that we're going to go to if we have a saturated substance, if we're under that vapor dome, if we're in that two-phase region. And it's going to be under the dome or on the dome. So if you have a saturated liquid or a saturated vapor, so you're right on the saturated liquid line or saturated vapor line, you're also going to look in those saturated tables. You have these organized by temperature and also by pressure. The nomenclature on here, A2 and A2E, E being English units, A3 and A3E. If you're looking in Xi books, they have a different nomenclature or a different numbering system for those tables. But in the PDF that you have access to on Canvas, those are the table numbers that are being used, and that's the numbering system that I will refer to. Okay. All right, so here's A2. This is for saturated water. It is organized by temperature. And I'm just going to be looking at those first four columns. So let's just look at those first four columns. I've got temperature, pressure, and then I've got two columns dedicated to specific volumes. So temperature, pressure, and that pressure is our saturation pressure at whatever that temperature is, right? So if I look at my TV diagram and I draw a line of constant pressure there, well, that pressure is the saturation pressure at whatever T1 is. So let's say T1 is 10 degrees Celsius. Well, that Psat at T1 is going to be this number right here, 0.01228 bar. Okay. Alrighty. So now let's look at our specific volume. We've got two things there, V sub F and V sub G. Remember, in your two-phase region, you have two phases, right? You have some amount of saturated liquid, some amount of saturated vapor. Maybe it's all saturated liquid if you're on that saturated liquid line, or all saturated vapor if you're on that saturated vapor line. But you've got some amount of each of those. Okay. Well, the V sub F is the specific volume that is associated with the saturated liquid, and the V sub G is associated with that saturated vapor. So if you're right on the line, if you're a saturated liquid and it's right on that saturated vapor line, or saturated liquid line, you would use the V sub F value. And if it's on the saturated vapor line, you'd use the V sub G value. And we'll talk later about what we'll do if we're somewhere in between there. Okay, so let's go look at our TV diagram. If we're at 8 degrees Celsius, and I'm going to draw a line of constant pressure through there in just a second. But if we had a saturated liquid, right, and so we're on that saturated liquid line, well, the specific volume there would be equal to the V sub F value. Yeah, now I want you to notice this is 0.00100002, because this number that's in the chart here has already been multiplied by 1,000. That's what that means right there. So it's not 1.0002, it's 0.00100002 meters cubed per kilogram. And then if I were on that saturated vapor line, well, it'd be this number right here, 120.917 meters cubed per kilogram. This has not been multiplied by anything. Okay. And then if I wanted to draw a line of constant pressure through there, that would be the saturation pressure. Okay. So it's all that stuff. It relates to the TV and the PV diagram. I could also do it on a PV diagram if I wanted to, but let's not for now. Okay. Table A3, exact same information. It's just organized by pressure. Okay, so sometimes it'll be more convenient to use a table A2, sometimes A3. Again, it's the same information, it's just organized a little bit differently. Okay. Okay, so for table A3, we've got pressure in one column, we've got temperature in the other. Let's just look at those first 4 columns because that's what we're going to use. So pressure, temperature, and specific volume. Let's say that we're at 0.10 bar. So here's my PV diagram just to kind of get our heads in the game here. And if I had a saturated liquid at 0.1 bar, well, the only specific volume that it could be is this number right here. And remember, it's already been multiplied by 1,000. If I had a saturated vapor, then it would be 14.674. That would be my specific volume. And then if I drew a line of constant temperature through there, it'd look like this. Okay, and that would be corresponding to that saturation temperature, right? Because 45.81 degrees Celsius is the only possible temperature that you could be at in that two-phase region if it were 0.1 bar. All right, easy peasy. Let's go to what if we're compressed. Let's look at those compressed tables, okay? Oops, there we go. All right, these are super easy. They're organized in blocks. Okay, and really you just have one page of these compressed tables for water, but they're very easy to read. You just go to the box that corresponds to the pressure you're at, and then you read off whatever value you need. So super easy. Again, that specific volume has already been multiplied by 1,000, so just kind of be aware of that, right? So you've got various pressures here that you can look at. Let's look at the saturated. Okay, we'll look up some values here. All right, so 2.5 megapascals, 180 degrees Celsius. We would figure out that this is compressed, and we'll figure out in just a second about how do we determine if it's compressed. But let's say for the time being that we know it's compressed, and let's go to our tables and pull out that specific volume. So in my compressed tables, 2.5 megapascals, which is the same as 25 bar. And I would just read off at 180 degrees Celsius what the specific volume is, right? So 1.1261 meters cubed per kilogram. Easy peasy. I'm sorry, 0.00. I did it, didn't I? 0.001261 meters cubed per kilogram because it's been multiplied by 1,000 already. So easy peasy. That temperature up there is the saturation temperature at 25 bar. So you'll notice that that's going to be the last row that's on this box corresponding to compressed liquid water. So at 25 bar, right, as we go up 20 degrees, 40 degrees, 80 degrees, we can only go up so high until we move into that two-phase region, and that will occur at the saturation temperature. So all right, let's look at our superheated water tables. These are organized very similarly. So this is table A4 and A4E. And when I say they're organized very similarly, I mean they're organized in boxes of pressure. Okay, so you just go to the box that corresponds to the pressure that you're at. So let's say that we have water, it's at 35 kilopascals and 200 degrees Celsius, and we figure out that it's superheated. Again, we're going to do that. We're going to figure out how to figure out what phase we're in a second, but let's go ahead and say we've figured out that it's two-phase. All right, so we need to figure out our specific volume. I figure out that it's two-phase, and I go to the tables, to my superheated tables. So I'm going to A4 because we're in English, and we're in SI units, not English units. So A4, not A4E. And then I would just go to the box that corresponds to 35 kilopascals, or 0.35 bar, or 0.035 megapascals. Okay. And then I would just read off at 200 degrees what the corresponding specific volume is. So easy peasy, 6.228 meters cubed per kilogram. All right. I told you that we would figure out, how do I figure out what the phase of the substance is? So let's do that right now. All right, so we have already talked about the state principle, but I want to revisit that real quick. All right, so remember the state principle says for a simple compressible system, we need two independent intensive properties to fix the state of the system. Simple meaning that it's simple. Nothing crazy going on in our system. Compressible meaning that the specific volume can change. Intensive, we know what intensive means. Independent of the size of the mass of the system. So temperature, pressure, and specific volume all check the box. And independent, well, we have to be careful here. Temperature and specific volume, always independent. Pressure and specific volume, always independent. Temperature and pressure, only independent in a single phase. And we used a TV and a PV diagram last time to sort of illustrate these points down here, but we're going to look at the tables and kind of show that as well. So let's see. All right, so to figure out the phase, or to figure out to use the table, we need to figure out the phase. And let me kind of go back to this point right here. So temperature and pressure, it's only independent in a single phase, meaning that if we're in a single phase, temperature and pressure are going to be enough to fix the state, but if you're saturated, it won't be. And so you could see that if you look at the saturated tables, right? So if I am given information that tells me, all right, you have water, it's at 6 degrees Celsius and the pressure is 0.00935 bar. Great. I know I'm saturated, but I don't know if it's a saturated liquid or a saturated vapor or somewhere underneath the dome. I don't really know. I need some other information. Okay. All right. So getting back about figuring out what phase we're in. So to use the tables, you need to determine the phase. So the first thing that we're going to do is we're going to look in those saturated tables, and we can look at the ones that are organized by temperature or pressure. And we're going to use the information there to figure out what phase we're in. So just because we're starting by looking in the saturated tables doesn't mean that we're saying, oh, okay, I'm going to assume it's saturated and then go from there. No, we're using the information in those saturated tables to figure out what phase we're in. Okay. And then we're going to go to the appropriate tables. If we just happen to be saturated, well, great, we're already there. But if we're not, then we'll go to the appropriate tables. So here's some rules that we're going to follow. And I would suggest memorizing this. I'm going to come back to this, but I want you to take a screenshot or have this somewhere where you can look at it and reference it as we go through the rest of this. So let's do that now, all right? So let's start with the two-phase substance. If you have a two-phase substance, if you're at the saturation pressure, or if you're at the saturation temperature at a given pressure, well, it has to be saturated. If you're at the saturation pressure at a given temperature, you have to be saturated. If your specific volume is between the V sub F and the V sub G value at a given temperature or pressure, then you're saturated. Okay. If it doesn't fall under that category, maybe a compressed liquid or a superheated vapor, okay? Yes, it could also be a solid. We're just focusing right now in that compressed liquid, saturated, and superheated vapor region right now. Okay. All right. So if your temperature is less than the saturation pressure, if your temperature is less than the saturation temperature at a given pressure, you're compressed. If your pressure is greater than the saturation pressure at a given temperature, then you're compressed. And if you're less than that specific volume that's associated with the saturated liquid portion, then it's compressed. And then it's opposite for the superheated vapor. So let's start working through some problems, and hopefully it will make a little bit more sense as we go through. All right, so we have water. It's at 10 degrees Celsius. We have a specific volume. They don't say it's specific volume, but those are the units for specific volume. 50 meters cubed per kilogram. Is it compressed, saturated, or superheated? And we want to know what's the pressure. Okay, so I'm writing down what my substance is and what I know about it. So best thing that you can do is try to figure out as quickly as possible what are the intensive properties that I know. And the intensive property list that I have right now: temperature, pressure, and specific volume. Those are the three that I'm familiar with. So I am given temperature and specific volume. Great. I need to figure out the phase and the pressure. So first thing I'm going to do, I'm going to start by looking in those saturated tables, not because I'm assuming that it's saturated, but because I'm going to use the information there to figure out what phase I'm in. All right, so let's look at the one that is organized by temperature, because I'm starting with temperature, so might as well look there. And I can see that at 10 degrees Celsius, well, let's look at that specific volume. It sure looks like it's between that V sub F and V sub G, which would indicate that it's saturated by my rules. But let's look at a TV diagram to show ourselves or prove to ourselves that is the case, okay? So here's my vapor dome. Here's the temperature, 10 degrees Celsius. If I draw a line of constant pressure there, corresponding to the saturation pressure at 10 degrees. Okay, so 0.01228 bar. And then I'm going to put our specific volume values there as well. So this is the specific volume that's associated with the saturated liquid portion at 10 degrees Celsius. V sub G is associated with the saturated vapor portion at 10 degrees Celsius. And we could see that we're between that, right? It's not exactly right in the middle, but it's pretty close to in the middle there. There you go. Has to be saturated, right? And then the pressure has to be the saturation pressure. And so I know by my rules, it is saturated. And so the only possible pressure that it could be at is going to be the saturation pressure. All right, easy peasy. Let's look at another one. So we have 100 degrees Celsius, 1 bar. We want to figure out, same thing, is it compressed, saturated, or superheated? And then we'll figure out the specific volume. All right, so I'm going to write down what are the 2 independent properties that I know and then figure out the specific volume and the phase. Well, the phase, then the specific volume. So I'm going to look at my saturated tables and I can see, and it doesn't matter, by the way, I pulled out table A2, but I could have also looked in table A3. Remember, A2 is your saturated tables that are organized by temperature. A3 is the saturated tables that are organized by pressure. I just picked out A2. It doesn't matter, but A3 would also give you the same information. So table A2 at 100 degrees Celsius, I can see that the pressure would have to be 1.014 bar in order for it to be saturated. I'm at 1 bar, kind of close, but not exactly. So that means that it's not saturated. So let's reason out what phase that it has to be. So I'm going to look on my TV diagram here. So at 100 degrees Celsius, and I'm going to draw my line of constant pressure where my saturation pressure would have to be, but I'm not at that saturation pressure. I'm not at 1.014 bar. I'm at 1 bar. So, and actually, let's kind of take a look at those numbers and notice, I'm going to go back to my chart over here. Those correspond to the V sub F and V sub G values, okay? All right. So I am not at 1.014 bar. I am actually at 1 bar. So, well, I can see that that puts me in that superheated region there, okay? So by my rules, what rule told me that, right? Without having to draw it on a TV diagram. Well, so let's see. I have my pressure is the second one right here. So my pressure is less than the saturation pressure at 100 degrees Celsius. In other words, my pressure, 1 bar, is less than the saturation pressure at 100 degrees Celsius. So that would tell me that it's a superheated vapor. It's on the right-hand side of that vapor dome. And so now I just need to go to my superheated tables. So if I looked at my superheated tables, 1 bar, 100 degrees Celsius, I'm going to go to the box corresponding to 1 bar and just read off the value there. Perfect. Easy peasy. All right, so let's go to the next guy. We've got water, 100 degrees Celsius, 50 bar. Is it compressed, saturated, or superheated? And what is the specific volume? So, all right, so I'm going to write down the temperature and pressure. Note that it's water, right? Because even though we're only messing with water right now, and that's the only tables we're looking at, just kind of keep in mind there are other tables for other substances. All right, so first things first, start by looking in those saturated tables to figure out what phase we're in. So we are at 50 bar, and 100 degrees Celsius. Now you'll notice, unlike the previous problem, now I'm looking at table A3. Could I have looked in A2, right? The saturated tables that are organized by temperature? Absolutely, that would be fine. It would tell me the same thing. So either one is convenient here. But so I'm looking at my table A3, which are properties of saturated water organized by pressure. And I can see, oh, I'm not at that saturation temperature, am I? So I know it's not 2-phase. Well, what phase is it? Well, I'm going to figure out, I'm going to reason it out, I guess. I could go back to those rules, which I will have memorized, or I could reason it out, right, on my PV diagram. So I'm going to draw a line of constant pressure. For 50 bar, I'm going to draw a little line of constant temperature, which corresponds to the saturation temperature, right? Because it's straight across at 50 bar in this two-phase region. So that's 264 degrees Celsius, 264 degrees Celsius. The V sub F value and the V sub G value. So this is the specific volume that's associated with the saturated liquid at 50 bar. This is the specific volume V sub G that's associated with the saturated vapor portion. Okay, well, I am clearly not in the two-phase region. I'm at 100 degrees Celsius, so let's draw a line of constant temperature corresponding to that. And I could see that that crosses over that 50 bar line in the compressed region zone. So the rule that would tell me, what phase that I'm in, well, so 100 degrees and 50 bar. So let's see. I could have said at 50 bar, the saturation temperature is 264. So my temperature is 100. So 100 degrees is less than 264 degrees Celsius, right? I would encourage you, go look in table A2 and see if you can justify it as well. And what would tell you that if you looked in table A2, you would get a saturation pressure at 100 degrees Celsius, and your pressure, 50 bar, should be bigger than that. Okay. All right. Well, let's go to those compressed tables. It's compressed. Let's go look for the compressed tables. So let's see, 50 bar, 100 degrees Celsius, right there. There we go. So it's going to be 0.00010410 meters cubed per kilogram. Easy peasy. All right. Almost there. I know this is a long one, but we're almost there. This is an important one. All right, so let's say that we are in that two-phase region. We know it contains some mixture of saturated liquid, saturated vapor, maybe all saturated vapor, or maybe all saturated vapor, but some mixture of the two, even if the amount of the other one is 0. We have if we're in that two-phase region, we have this V sub F and V sub G value that we've been talking about. So which one do we use? And the answer is it's going to be based on both of those. Okay, so quality. This is another intensive property. So right now we have 4 intensive properties that we're familiar with. We have temperature, we have pressure, we have specific volume, and now we got quality, right? All right, so let's look at our little video here. So this is looking at a phase change, a constant pressure phase change, as we go from a compressed liquid to a superheated vapor. Okay, so we've sort of talked about this process before when we were talking about the saturation pressure and saturation temperature, right? At a given temperature, there's only one possible pressure that you could be at and be two-phase, right? So that corresponds to this guy right here. Well, let's kind of look. As we hit this saturated liquid line, we start to go through a phase change. And we go into that two-phase region, and we have two things there, gas and liquid. And as we move to the right, we have more and more gas and less liquid, okay? So quality is going to tell us something about that ratio. All right, so if we're on that saturated liquid line, we have 100% liquid, okay? As we move forward, or as we move to the right, we get more and more gas and less liquid until we get to the saturated vapor side, and it's all gas. It's all saturated vapor, okay? The quality is the ratio of the masses, okay? It is the percent by mass saturated vapor. So the subscript F indicates that it's associated with the saturated liquid. Subscript G associated with the saturated vapor. So M sub G is the mass of the saturated vapor in that two-phase substance. M sub F is the mass of the saturated liquid in that two-phase substance, okay? Because there's only two phases, right? Saturated liquid, saturated vapor, add them together, it has to be the mass of the whole thing, right? So it's M sub G over M. That's our quality. Okay, So you can calculate, you can use that quality to calculate that specific volume, and it's going to be sort of a weighted average of the V sub F and the V sub G contributions. Okay, so it's V sub F plus the quality times V sub G minus V sub F. Sometimes you'll see properties with an FG. That just means it's the V sub G minus V sub F, or the property sub G minus the property sub F, depending on if it's another property or not. But the F sub G indicates G minus F, V sub G minus V sub F. Sometimes you get a table that tabulates that, so it's just important to know what that represents. If your quality is 0, that means you don't have any saturated vapor, so M sub G is 0. If all you have is saturated vapor, well, then these M sub G and M are equal to one another, so it's going to be 1. So that quality goes between 0 and 1, and it is only defined in that saturated region. So even though, you could say in the compressed region, you could say, oh, well, I don't have any saturated vapor, so M sub G is 0. It's not defined there because it doesn't mean anything. It only has meaning in that two-phase region. So it would be incorrect to say that compressed liquid has a quality of 0. Okay, because you could also look at this part right here. In a compressed region, no, you don't have any M sub G, but you also don't have any M sub F. So it would be undefined, right? All right, so let's use that quality. What is the temperature and quality of water at 10 kilopascals and 10 meters cubed per kilogram? Well, let's go look at it. All right, so first thing I have to do, figure out what phase we're in. So we're at 10 kilopascals or 0.1 bar. And I can see that my specific volume is between the V sub F and the V sub G. So, well, that's fantastic. That means it's two-phase. Great. I don't have to go anywhere else. This is the table for me. I am in the right table. So I know that the saturation temperature, it has got to be the temperature, right? Because if I'm saturated, which I've already figured that out, right? I know that I am. The only possible temperature is that saturated temperature, which is 45.81 degrees Celsius. Now I also need to figure out the quality, and I do have a formula for quality that's dependent on the V sub F and the V sub G values. I just need to make sure that I note that this V sub F value has already been multiplied by 1,000, so it's not 1.0102, it's 0.00100102. Okay, so my quality ends up being 0.681 or 68%. Perfect. Little word to the wise, if you calculate a quality that is greater than 1, you screwed something up. It can't be greater than 1. Okay, and you probably have incorrectly fixed your state, and you need to go back a step. Okay, so just be aware of that. Okay. Whew. That was a long one, wasn't it? But we got through it. Hopefully that was helpful. Thank you for watching. Please let me know if you do have questions.